Hi, in this video we're going to take a look at question 9 from 2017 higher level paper 2. So in this case we're told that Connor's property is bounded by a straight bank of a river as shown in figure 1. So this is the figure, this is the river, a couple of points, and those points are related to each other as on the diagram. So CT are along the straight line. There is a right angle here between DC and CT. This is segment DT, so it's a straight line again. And we have a tree which grows from T, and the top of the tree is given by point E. And also there is some relationship from E to C. And point F, which is going to be needed later on. Anyway, use triangle ECT to express T in the form root A of CT. So in this case, I guess we kind of need to take a look at this angle here, angle 60 degrees. And if I just redraw this third triangle here, so this is CT, this is C, this is T, and this is E, and this is 60. So tan 60 is the same as ET over CT. ET or TE, same difference. So if that's the case, TE is equal to tan 60 by CT, and that's given by root 3 times CT, and obviously this has to be length of CT, so root ACT. Now then we need to show that T may also be expressed using this formula. So okay, let's have a look how this formula. It's kind of difficult enough to figure out how to get to that formula, but let's maybe take it step by step. So I already kind of looked at this side of the triangle, so maybe I could take a look at the bottom of this triangle and then figure out whether I can use the tan of angle 30 degrees. So I can say that tan 30 is equal to, from my diagram, is equal to TE over DT. So let's write that down. That's equal to TE over DT. So TE, length of TE, is equal to tan 30 times DT, length of DT. So tan 30 is 1 over 3, so that would be dt all over root 3. Okay, so let's figure out how can we get dt from here. So dt from the CTD triangle, dt is equal to 15 squared plus length of CT squared. So let's just write that down. dt is equal to root of 15 squared plus length of CT squared, and that equals to root of 225 plus length of CT squared. So now I can put that formula back into my original equation in here and get that length of TE is equal to square root of 225 plus length of CT squared, and all that over 3. Note that this is all under the same square root. So happy days. Now I want you to find the length of CT, the distance from the base of the tree to the bank of the river on Connor's side, giving the answer correct to 3 decimal places. So that's kind of straightforward enough, actually, all things considered, because I can use this formula here. So let me just rewrite it. TE is equal to root of 225 plus CT squared all over 3. Replace this with root 3 CT. Root 3 CT is equal to, again, just rewrite this here, 225 plus CT squared all over 3. Now I can square both sides and get 3 then CT squared equals to 225 plus CT squared, all that over 3. Multiplying both sides by 3 to get rid of the fraction, I get that 9 CT squared is equal to 225 plus CT squared. So then bringing everything to the same side, I get that 8 CT is equal to 8 CT is equal to 225 and also CT squared actually. So CT is equal to square root of 225 all that divided by 8, which gives me the value of 5.303. And then to get the length of TE, I'm going to go back to the previous equation. TE equals to root 3 CT, which is equal to root 3 by 5.303, and that gives me a quantity of 9.2 meters. Which is equal actually here 5.3, correct to 1 decimal place. So then the tree falls across the river and hits bank at corner side at point F. We have to find the maximum size of the angle FTC and give our answer in degrees correct to 1 decimal place. So if I just look back on the diagram again, the maximum value of that angle is when the tip of the tree just about hits point F. So if I draw that angle and connect the base of the tree with point F, the cosine of that angle alpha will be equal to CT over TF. So let me just write that down. Cos alpha equals to CT over TF, and obviously TF has to be equal to T because the maximum value of the TF is the height of the tree, so that will be CT over TE. That gives me just the subbing values in CT over root 3 CT. So that turns into root 3 over 3 is the value of that cosine. So alpha is equal to cos minus 1 of root 3 over 3, and that equals to 54.7 degrees. Now if the tree was equally likely to fall in direction, find the probability that it would hit the bank on the corner side when it falls. Give your answer as a percentage correct to 1 decimal place. So here we need to recognize that the angle that the tree can make when hitting the river on corner side is equal to twice my angle alpha. So this is 2 alpha. And the probability will be the value of 2 alpha divided by the value of any possible angle, which is 360 degrees. So that will be equal to 100 and 109.4 divided by 360, and that gives me a quantity of 0.304, 0.304, which is equal to 0.3 correct to 1 decimal place. And that concludes question 9 and concludes solutions of 2017 higher level maths paper 2. Thank you for watching.